In this video, we're going to use Google Sheets to set up some kind of calculator machines that will compute confidence intervals for either a single, right, one sample proportion, or a one sample mean, where we're calculating the mean of our sample, and we have raw data, or the situation where we're calculating the mean of our sample or the confidence interval for the mean of our sample, and we're given the actual statistics instead of the raw data. Okay, so if you have access to my template, you will have what you see on the screen along with a lot of other stuff. I've basically deleted out all the other stuff just so it's not a distraction, because these are the three that we're going to be concentrating on in this video. And if you don't have the template, then just pause the video and basically recreate what you see here. Also, of course, if you're using Excel, some of the command ribbon up at the top will look slightly different, right? This stuff up here will look different, but it all has the exact same functionality. So it doesn't matter if you're in Excel, a standalone, or Office 365, or if you're doing Google Sheets. Everything we're going to be typing into these cells should be exactly the same. Okay, so now that you have yours set up to look like mine, we just have to remember that everything that's highlighted in yellow is the information that we're going to change for each new question that we come across. So each new homework question, a quiz question, test question, whatever, the information that they give us, we will put into the yellow cells, and then everything else will get auto-generated based on that new information. So the first thing we need to calculate is our probability of a success. And our probability of a success is very simply calculated as the number of successes in our sample divided by our sample size, i.e. it's just k divided by n. So it's just going to be equals, click on the cell where the k is, / for division, click on n, hit enter, and there's k divided by n. And we can see that 150 over 200, if we did that math, that's 75%. If you wanted to, you could change the formatting of this to display it as a percentage, which is what I've done up here, by the way, is I have clicked up here to format this as a percent. And the nice thing about doing that is when you have a question, let's say it goes, okay, now you need to do 90%. I just need to type in 90. I don't have to put in 0.9, right? Because if I put in 0.9, it's going to give me 0.9%. And that's not good, right? I want 90%. And that's, so you want to make sure that it's formatted as a percent. And then that way, you don't have to worry about typing in the decimal equivalent of whatever percentage you're dealing with. Okay. Now, Q is always just 1 minus P, so we can literally just do equals 1 minus, and click on the cell where P is, and there's my 25% to go with 75%. Okay, your alpha is your error rate, which is always 1 minus your confidence level, so that's equals 1 minus my confidence level. So there's my alpha, and I've also formatted this as a percentage. Now your Z critical level, this is the number that you have to put into your function to get your Z. Because we're leading ourselves down the path so that we can calculate our margin of error, our E here. And we can see in the formula, we need this Z of alpha over 2. And the reason why we call it alpha over 2 is because alpha is our error rate, right? In this case, it's 95 minus, or 100 minus 95 gives us the 5% error. So it's alpha is 5%. But the Z score that we want has to have half of that error above it, because the other half is in the lower tail. Because remember, the Z score always corresponds to a percentage of area that's to the left, that's below it. So if we're looking for that confidence interval that is centered in our normal curve that has 95% of the area, then there's 2.5% above that interval and 2.5% below that interval. So the little z-score that's sitting in the upper right hand, right, that basically gives us the upper bound of that area, will only have 2.5, half of the alpha above it. So that's what we're doing here is we're basically calculating the to the left of it, right? If there's 2.5 above, there's going to be 97.5 below. So that's where we get the confidence level of 95 plus half of alpha. So 95 plus 2.5 gives us 97.5. So this is going to equal the confidence level plus this divided by 2. And of course, it's not 98, it's 97.5. So if we just want to show more decimals, right, then we can see, okay, then it's doing it correctly. Now, of course, none of this is necessary. We could do all those computations within the actual, z function. But I'm just doing this so we can kind of remind ourselves of how the math works and where the numbers are coming from and all that kind of stuff. But as you get better at this, you can compute all this stuff within these functions and tighten this up, right? Make your calculator, maybe only 4 lines instead of the 9 or 10 that we have here, kind of thing. Okay, so we now want to calculate our z-score, right? A z of alpha over 2 is basically a z-score on the normal curve. So we're going to do the equals norm dot inverse function, because we're not doing norm dot distribution. Norm dot distribution is when we give it a z-score, right? We give it a value and it tells us what percentage of the area is to the left of that value. The norm dot inverse function says you give me a percentage, i.e. the 97.5%, and I'll give you the z-score that cuts off that much area below it. So the first number it wants is the percentage, comma. The second number it wants is the mean and then the standard deviation. But since we're looking for a z critical, which is on the standard normal curve, we use the mean and standard deviation of our standard normal curve, which is a mean of 0, comma, standard deviation of 1. Close our parentheses, and then there is my score. And you can't really see it because it's showing too many decimals, so I'm going to decrease my decimal places down to, let's just say, 4 of them. And then now we can see it's 1.96 roughly. You saw it was 1.95996 and so on and so forth, right? Okay. But in any case, that's my z of alpha. Now, finally, for the big grand finale, at least as far as the margin of error is concerned, I just have to recreate this formula in this cell. So it's going to equal my z of alpha over 2. That's that cell. Times, so that's asterisk, square root, so SQRT, that's the function. Oh, I put AQRT, SQRT. See, there it is, the square root function. Then the value, what goes in the square root? Well, in the square root, I've got p hat times q hat divided by n. That's so p hat asterisk q hat divided by n, my sample size, up here. Close that square root, hit enter, and again, we can't see it, right? We gotta show a little less accuracy. There we go. And there's my margin of error. Now, you might have been thinking, well, didn't I need parentheses around the p hat, q hat so that, the whole thing was being divided by n? Yes, if there was an operation up there other than multiplication, but because multiplication and division are basically the same operation, right? They're inverses of each other. They're on that same level when we talk about order of operations, the PEMDAS. So we don't need that because the way order of operations works, it knows to do all multiplication and division together as a clump. So you didn't need parentheses. You could have, and it wouldn't have made it wrong. They were just unnecessary at that point. Of course, if it was p plus q divided by n, then you would, right? Or p minus, that kind of thing. But in any case, so there's our margin of error. Now, we need to do the lower confidence interval and the upper confidence interval, and the lower confidence interval is simply just the single point estimate minus our margin of error, and in this case our single point estimate is our probability of a success, our p hat, so it's just going to equal p hat minus our margin of error, and then this one is going to equal p hat plus our margin of error. And then down here, you can see I set up something that kind of writes our interval in interval notation, but there's way too many decimals. So I can go in here and I can round this off, round this to, let's say, 4 decimals, and then do the same thing with this number. Round it to 4 decimals, and then there is my confidence interval written as an actual confidence interval. Now that's a total advanced thing where I'm just showing off, right? As long as you have these answers, that's all that matters. Okay, so that's for one sample proportion. You can see that we're basically going to do a lot of the same thing for the mean. We're just going to be doing it based on numbers instead of proportions. Now, in this example, I have a set of data that I loaded into column D. Remember that whenever we're doing repetitive computations on a column, we need to make sure that we define our programs in Google Sheets to calculate all the numbers in that column. So when you go to replace this, you have to make sure that you delete the entire column, right? Clear the whole column out, then paste your new data set in there. Because if you just, like, let's say, just pasted some data here, all these remaining numbers below are still going to be there. So you just have to be careful with, how you put your data in and out. Okay, so the first thing we need is our sample size, i.e. how many pieces of data we have, and that is the equals count. That's the count function, right? It's the number of numeric values. So we're going to choose count, and then we're going to click on D because we want it to count everything in column D, and you'll see that it just puts D colon, not semicolon, but full colon D. And so that counts everything. So we have 36 numbers. You'll notice that you won't notice because you don't know it ends down there at row 37, but it's not going to count data because data isn't the number. That's the nice thing, is we could still have, we could say what this data is, weights or, ages or whatever, and it's not going to count that because the count function only counts numbers. Same thing with the next one, right? We need the average. So equals the average. Click on average, and again, just click on D because we want the entire column. I'm going to, once again, change how much it shows just so I can actually see the number. Do the same thing, equals standard deviation of a sample, right? Standard dev.s, because we're going to assume this is a sample of data. I mean, it's pretty rare that we have a population of data. If we did, we'd have to kind of change that. But click on D because we want the whole thing. Okay. And so now we pretty much have everything that we had before as far as, numbers are concerned. And then we just have to do kind of the same thing, the alpha and the t and so on and so forth. So here's our alpha level. And in this case, we're just going to do the same thing. It's the error rate. It's just simply equals 1 minus confidence level. Simple and easy. Same thing. Now we're doing a t critical level instead of a z critical level. It's the same darn thing, only now we're doing it on the t curve instead of the z curve because we're dealing with averages, and we do not know the population standard deviation, which is usually the case. So this is going to equal, same thing as before, confidence level plus alpha divided by 2. And both of these, I'm just going to give myself a couple more decimals to see exactly, that it's not rounding. But again, it wouldn't matter. Degrees of freedom, that's always your sample size minus 1. So equals sample size minus 1, simple and easy. Okay, now we're going to do our t-score. So just like we did a z-score over here of z of alpha over 2, we're going to do a t of alpha over 2. So instead of the z inverse, this is going to equal the t dot inverse function. The first thing it wants is the probability, i.e. the amount of area to the left. So that's that. And then comma, degrees of freedom, that cell that we just calculated. And there is our t-score. Show 4 of them, what the heck. And then, same thing as last time, calculate our standard error, or sometimes called, it's actually margin of error, by the way. right here, this times this times this. So equals t, right, t of alpha, times s, that's our standard deviation, so that cell, divided by the square root of n, so sqrt for square root, and then click on n for our sample size, and there we go. That's E. Again, make it less decimals so we can see what it is, and then just like before, right? And here's the nice thing about Excel. We already asked it to create these things over here. If I just highlight these, do Control C, come over here and do Control V, it repeats the pattern, because the pattern was take this number up here and subtract that one from it. That's not going to work here, because if I go up the same amount, it's doing the standard deviation, right? So you got to be careful. It'll repeat patterns, but it's not smart enough to repeat it with the right thing. It doesn't know to grab the mean this time. But if we go equals the mean minus this and equals the mean plus standard error, and there we go. We can see that our mean was 44 minus 3.5 brings us down to that and up to that, and so there's our lower and upper. Now here's where copying and pasting works, because you can see over here we're given the stats. So instead of having a set of data, we're told our sample size was this, the mean of our sample was this, the standard deviation of our sample was this, and then all of these cells mirror those. So all we have to do is highlight this, do Control C, come over here, Control V, and it's now calculated everything in the proper place. You can see that 95, there's half of it, right? Or so the complement, that's 95 plus 2.5, and there's my degrees of freedom, 11 minus 1, and so on and so forth. That will now enable you to calculate confidence intervals for both a one sample proportion and a one sample mean.